Hey everyone, my name is Kingsley, and today I'll be talking about applications to cycloids and other special parametric curves.
So the example I chose to illustrate this is example 3, which says find the area under one arc of the cycloid x equals r times theta minus sine theta and y equals r times 1 minus cosine theta. But before we start solving this problem, we need to clarify a few things. So what is a cycloid? A cycloid is the path created by a point on a circle as that circle rolls on a straight line. So as you can see from this graph, it's kind of like if you were bouncing a ball and it was just like dribbling on and on and on. And cycloids do have parametric equations, which are given in the form x equals r times theta minus sine of theta, and y equals r times 1 minus cosine theta. And r is the radius of the rolling circle, and theta is the angle of rotation. And since we're trying to find the area under a parametric curve, we need to use the equation a equals the integral from a to b of y dx, or it can be given in the form the integral from alpha to beta of g of t times f prime t dt. And this is the graph of our cycloid, which comes from these parametric equations. And when we graph them, we see that one cycloid goes from 0 to 2 pi r, so we would want to find the area from 0 to 2 pi r. And the final two things we need to start solving this problem is y and dx, and we already have our y value from the problem, which is r times 1 minus cosine theta, and dx would be the derivative of the x equation we were given, which would be r times 1 minus cosine theta d theta. And now we plug everything into the area equation, so we set our parameters from 0 to 2 pi r, and we have it right now in terms of x, but then when we plug everything in, it's going to be in terms of theta. So we need to change our limits to be of theta. So it becomes from 2 pi r to 2 pi, since at 2 pi, our radius is 0, since we're right on the x-axis, and then 0 is just still 0. And so our new integral is the integral from 0 to 2 pi of r times 1 minus cosine theta times r times 1 minus cosine theta d theta. And what we can do here is pull these two r's and put them on the outside since they're both constants. So we have r squared times the integral from 0 to 2 pi. And now that we've gotten these two r's out, we're left with 1 minus cosine theta times 1 minus cosine theta. So we can just simplify that to 1 minus cosine theta squared d theta. And now, after we multiply this out, we are left with 1 minus 2 cosine theta plus cosine squared theta. And this is pretty hard to integrate, and we can use a trigonometric identity to turn it into 1/2 times 1 plus cosine 2 theta. And we can also distribute this 1/2 to these terms in here, and we're left, and this integral now becomes 1 minus 2 cosine theta plus 1/2 plus 1/2 cosine 2 theta d theta. Now, all we have left to do is combine like terms here. So we get 1 plus 1/2, which is 1/2 or 1 and 1/2 or 3 over 2. And then, yeah, that's it. And then after we integrate, we end up with 3 over 2 theta minus 2 sine theta plus 1/4 sine 2 theta. And then we plug in 0 and 2 pi, which we get r squared times 3 over 2 times 2 pi minus 2 sine of 2 pi, which is 0, 1/4 sine of 4 pi, which is equal to about 0. It's a really small number, but it's so small that we can just treat it as 0. And then when we minus everything, we're just multiplying it all by 0, and all of these terms add up to 0. So what we end up with is r squared times 3 over 2 times 2 pi, and since these two 2's cancel, we end up with 3 pi r squared as our final area under the cycloid.